Think about the last time you bought something online.
Oh, probably just a few hours ago.
Right, exactly. Maybe you're grabbing a new mechanical keyboard or, pre-ordering a book or just refilling your favorite coffee beans.
Yep.
You drop the item in your cart, you double-click the side button on your phone, and boom, it's done.
It feels incredibly frictionless.
Almost like magic, right?
Yeah.
But what actually happens in that split second between you clicking buy now and the website rendering that order confirmation page?
It's remarkably easy to take that split second for granted. I mean, it happens so fast.
It does.
And as users, we are totally conditioned to expect instant gratification. But beneath that simple user interface, there is an incredibly complex, highly secure sequence of API calls firing off behind the scenes.
It's a massive system.
It is. It's a synchronized system designed to be entirely invisible to you, the consumer.
Which brings us to today's deep dive. Our mission is to uncover that invisible, highly secure maze that powers modern online shopping.
And to map this out, we're looking at a stack of 4 highly technical developer manuals from a platform called Integrate Payments.
Right. Specifically, we are poring over their Quick Click guide, the Direct Post API, the Query API, and the 3-step Redirect API documentation.
Which sounds like a lot. And for anyone who spends their days in code editors, these API manuals are just a complete goldmine of architectural decisions.
Oh, absolutely.
But even if you don't write code for a living, understanding these mechanics gives you a VIP, behind-the-scenes tour of how your digital wallet actually functions out there in the wild.
We're basically translating the endpoints and, JSON payloads into the real-world mechanics of how your money moves safely across the internet.
Handling all the edge cases, the security protocols, and everything in between.
Okay, let's unpack this. We are going to start at the foundational level with what the developers call Quick Click.
The simplest route.
Right. If a merchant is running just a straightforward content site and wants to sell a single digital product or maybe take donations, they probably don't want to build a custom checkout flow from scratch.
No, that would be overkill.
Exactly. So Quick Click serves as essentially a no-code solution. The merchant uses a back-end generator to create a simple chunk of HTML code for a shopping cart button or a fixed price button or a donation button.
And they just drop that code straight into their website's DOM.
Just copy and paste.
Yeah, it's designed for maximum accessibility and speed to market. But the manuals detail how these simple HTML buttons don't actually have to look like generic, out-of-the-box payment gateways.
Right, they don't have to look clunky.
Exactly. Merchants can inject their own CSS-style sheets. They can specify HEX color codes to modify the text, the form fields, the headers, the background.
So the gateway generates the functionality, but the merchant styles the button so it looks totally native to their own site's branding.
Which keeps the user experience entirely seamless.
But, and this is a big but, anytime you rely on client-side HTML that lives right there in the user's browser, you open up a massive vector for manipulation.
Oh, yeah. The classic client-side vulnerability.
Because if a customer inspects the page source, what's stopping them from simply altering the HTML code, finding the hidden input field for the price, and, changing a $100 item to $1 before hitting submit?
Right. The documentation addresses that exact vulnerability head-on with a feature called key verification.
How does that work?
When the merchant generates that HTML button on the back end, the system utilizes cryptographic hashing.
Okay.
It takes the authorized price, the SEU number, and the specific shipping rules, and it runs them all through a one-way hashing algorithm.
Which creates a unique signature.
Exactly. A unique signature that is embedded right there in the button's code.
So it's essentially like a tamper-evident digital seal for the transaction.
That is a perfect way to describe it.
Yeah.
If a malicious user jumps into their browser's developer tools and alters the price variable to $1,
They break the seal.
they break the seal. When they click buy, the payment gateway receives the altered payload, hashes that new $1 price against the original secret key, and sees that the resulting signature no longer matches the one generated by the merchant.
And it just rejects it.
Immediately rejects the transaction. It's such an elegant way to secure a client-side button without requiring complex server-side validation for every single click.
It's brilliant in its simplicity, but Digging through the Quick Click guide, you also stumble into the mundane, pull-your-hair-out reality of modern web development.
Oh, you mean the iframe issue?
The infamous iframe issue. The manual explicitly warns developers that Quick Click buttons absolutely cannot be used inside iframes.
Yeah, and developers used to love iframes for payments.
Why is that?
Because it allowed them to embed the payment gateway's secure page directly within their own site's layout. It kept the user from feeling like they were being redirected to some third-party site.
Right, keeping them on the page.
But as the industry shifted toward aggressive privacy standards, browsers, specifically Safari, introduced features like intelligent tracking prevention.
And those features actively block third-party cookies by default.
Exactly. And because QuickClick relies heavily on those session cookies to track the cart state inside that embedded window,
Safari basically nukes the functionality.
completely nukes it. The browser treats the payment gateway's cookie as a cross-site tracking attempt and blocks it.
So what does the user see?
The result is a completely broken button or just a blank frame. The user can't even view the checkout.
That is brutal.
It's a perfect, frustrating example of how a well-intentioned privacy update in a major browser can just completely break a legacy payment integration.
Forcing developers to constantly adapt their architecture.
Exactly.
So if QuickClick is too rigid, and an iframe is a non-starter for merchants who want a highly customized, frictionless checkout flow, they have to abandon those simple HTML buttons.
Yeah.
What is the next step up?
That brings us to the Direct Post API. Direct Post is where the training wheels come off, and the developer takes full control of the state and the user interface.
It's engineered for merchants building complex, custom payment flows directly on their own infrastructure, right?
Yes. The manual outlines a standard four-step lifecycle. Step 1, the customer submits their payment info into the merchant's custom-built front end.
Okay.
Step 2, the merchant's backend server collects that data and POSTs it directly to the payment gateway's API endpoint.
Got it.
Step 3, the gateway processes the charge and responds with a success or decline payload. And Step 4, the merchant handles that response and renders the appropriate UI for the customer.
Wait, let me hit the brakes on step 2.
Sure.
If the merchant site is actively collecting the raw credit card data, the primary account number, the expiration date, the CVV, and passing it through their own backend to send to the gateway, aren't they basically holding a ticking time bomb of liability?
Yes. In the world of cybersecurity and compliance, that raw credit card data is effectively digital toxic waste.
Toxic waste. That's a great analogy.
The moment your servers, your databases, or even your application logs touch those 16 digits and the security code, you pull your entire infrastructure into the scope of PCI compliance.
The payment card industry data security standards. And Visa and MasterCard do not mess around with those rules.
They absolutely do not.
If you are handling that toxic waste, you suddenly have to undergo intense, incredibly expensive security audits.
Penetration testing, strict access controls.
And most importantly, you assume direct liability for data breaches. If a threat actor finds an unpatched vulnerability in your server and exfiltrates that toxic waste,
The financial and reputational ruin falls squarely on your shoulders.
which is an unacceptable risk profile for most businesses.
Completely unacceptable. To mitigate this, the API documentation introduces a critical architectural component.
The customer vault.
Yes, the strategy is to offload the toxic waste immediately. Instead of the merchant storing the PAN in their own local database, they transmit it via an encrypted TLS connection directly to the gateway's Level 1 PCI certified vault.
So they hand over the waste.
Right. The vault locks the sensitive data away on their highly secured servers and hands the merchant back a token.
And that token is just an alphanumeric string.
Exactly. It acts as a surrogate for the real card.
So if a hacker breaches the merchant's database and steals 1 million tokens, it's completely useless to them because those tokens cannot be mathematically reversed into credit card numbers.
Precisely.
But here's where it gets really interesting, because the documentation goes deep into how this tokenization architecture handles the tech most people use daily.
Apple Pay and Google Pay.
Yes. Digital wallets are essentially the ultimate evolution of tokenization.
They really are. When you authenticate a purchase with Face ID for Apple Pay, your device doesn't transmit your actual credit card number to the merchant.
No, it generates a dynamic, highly encrypted, cryptographic payload.
Right. In the API references, you'll see this handled with variables specifically designated for Apple Pay payment data or Google Pay payment data.
This is the part that fascinates me. When you use Apple Pay on a merchant's site, the merchant's server receives this encrypted payload, but they don't hold the decryption keys.
They can't even crack open the payload to see what's inside.
They are essentially acting as a blind courier, passing that encrypted token directly to the payment gateway.
Because only the gateway holds the private certificate required to decrypt the payload, extract the network token, and process the authorization.
But the API also handles edge cases for massive enterprise merchants who do manage their own Apple processing certificates, right?
Yeah, the ones who decrypt the payload on their end before sending it to the gateway.
And the manual details a brilliant developer hack here. To transmit that decrypted wallet data securely, they repurpose existing 3D secure fields.
It's very clever. They take the cryptogram generated by the digital wallet and inject it into a field called CAVV.
Which stands for Cardholder Authentication Verification Value.
Right, which is normally used as the cryptographic proof for 3D secure transactions. Then they pass the electronic commerce indicator through a field called ECI.
And that signals the security level of the transaction to the issuing bank.
It's a really smart way of utilizing existing authorization pipes to handle modern biometric wallet data without having to rewrite the entire network protocol.
Okay, so looking at the dilemma merchants face. QuickClick is simple, but offers very little control and gets blocked by modern browser privacy features.
Right.
Direct Post gives you total control over the DOM and the user experience, but it forces your servers to touch the raw data.
Triggering that massive PCI compliance headache if you weren't careful.
Exactly.
Yeah.
So is there a middle ground that provides the customization of Direct Post without the toxic waste liability?
There is, and it's heavily detailed in the 3-step redirect API documentation.
Let's hear it.
If we connect this to the bigger picture, this API is really a masterclass in secure data routing. It is specifically engineered to completely remove the merchant's infrastructure from the scope of PCI compliance, while still allowing the developer to build a totally custom, native-feeling checkout UI.
It's called the 3-step redirect. So let's break down the mechanics of those 3 steps, because the routing here is incredibly clever.
Step 1 happens entirely back-end to back-end.
Right. The merchant server makes a secure API call to the payment gateway. It passes along the non-sensitive context, things like the order ID, the total amount, the shipping address.
It essentially says, I'm about to send you a customer for a $50 transaction. Stand by.
And the gateway registers this intent and returns a unique temporary API endpoint, usually formatted as a form URL.
And that form URL is the linchpin of the entire operation.
Okay, what happens in step 2?
Step 2 shifts to the client side. The customer is on the merchant's website looking at a highly customized, beautifully CSS-style checkout form.
They input their raw credit card number and hit submit.
But here is the critical distinction. The developer has set the HTML form action to post directly to that form URL from step 1.
So when the customer hits submit, the sensitive payload completely bypasses the merchant's back-end server.
It is transmitted directly from the customer's browser to the payment gateway's secure environment.
The merchant server is completely blind to the transaction at that moment. The toxic waste flies right over their infrastructure.
Exactly. The gateway ingests the raw data, secures it within its PCI-compliant boundary, and then instantly executes an HTTP redirect,
sending the customer's browser back to the merchant's designated success or failure page.
Crucially, the gateway appends a temporary token ID to that return URL.
So the customer lands back on the merchant's site. The merchant's backend grabs that token ID from the URL, which brings us to step 3.
In step 3, the merchant server makes one final backend API call to the gateway.
It passes that token ID.
And effectively says, I see the customer return successfully. Execute the charge against whatever secure data you collected during step 2.
The gateway finalizes the transaction, and the loop is closed.
The user experiences what feels like a seamless single-page checkout, but their most sensitive financial data was actively routed around the merchant systems.
It drastically reduces the merchant's attack surface and regulatory burden.
Yes.
It is an elegant architectural solution for single, one-off purchases.
Yeah.
But what about the subscription economy?
That's a whole different beast.
So what does this all mean for recurring billing? If you subscribe to a SaaS platform or a monthly coffee delivery, how does the merchant legally and technically authorize a charge next month when the customer isn't interacting with the checkout form at all?
This ventures into some of the most stringently enforced rules in the payment processing industry, broadly known as credential-on-file mandates.
Right.
To navigate this, the API documentation draws a hard line between two transaction types, CIT and MIT.
Let's find those.
A CIT is a customer-initiated transaction. This is the active phase. The customer is on the device, authenticating the session, passing CVV codes, or using Face ID.
And an MIT.
An MIT is a merchant-initiated transaction. This occurs asynchronously. The merchant server triggers the charge while the customer is offline, asleep, or at work.
And you can't just spin up an MIT out of thin air. The card networks require an explicit cryptographic paper trail, proving that the customer consented to future charges.
That paper trail is non-negotiable. To process a recurring subscription or even an unscheduled variable charge like a cloud hosting provider billing you for bandwidth overages at the end of the month.
The merchant system must first capture a successful CIT.
Right. During that initial customer-present transaction, the API returns an initial transaction ID.
Furthermore, the developer must explicitly pass a flag in the payload, specifically setting the stored credential indicator to stored,
Alerting the issuing bank that the cardholder has agreed to keep this credential on file for future use.
and the documentation highlights how granular this tracking gets. When the merchant's automated job runs next month to process the MIT, the API request must include that exact initial transaction ID.
It is the cryptographic proof linking the background charge back to the original moment of user consent.
If the developer fails to map that ID correctly in the payload, the issuing bank's fraud models will likely hard decline the transaction.
And this strictness creates massive headaches when edge cases arise.
Like what?
Well, the manuals point out that the card networks operate as entirely distinct, siloed ecosystems. If a customer has a subscription tied to a Visa card, and that card is compromised, they might log in to update their billing profile with a new MasterCard.
Makes sense.
From a database perspective, the merchant just wants to update the PAN. But from a compliance perspective, they can't simply attach a new network brand to an old consent trail.
Oh, so that explains why updating an expired card on a subscription service often forces you through that annoying multi-step verification process.
Sometimes even doing a $0 authorization.
They have to start from scratch. They have to spin up a brand new CIT, generate a totally new initial transaction ID, and establish a new credential on file flag for the new card brand.
It forces the merchant to continually validate user intent. Now, when you scale this up to an enterprise level, millions of tokens, complex CIT and MIT linkages, retries on failed subscriptions, you start to understand the immense data management challenge.
A business needs to reconcile all of this activity.
And this is where the query API becomes the nervous system of the accounting department.
Because an enterprise accounting team cannot rely on static daily batch files. They need programmatic access to the raw data.
The query API acts as a highly optimized search endpoint directly into the gateway's transaction database.
The parameters available in the query API allow for incredibly precise data extraction.
Imagine a scenario on a Friday afternoon at the end of a fiscal quarter.
Always a stressful time.
The accounting team is staring at a discrepancy between their internal database and the bank deposit. They can hit the query API, passing parameters to filter exclusively for transactions tagged as pending settlement.
Instantly isolating the charges that haven't cleared the funding cycle.
Exactly. And the documentation shows they can filter by almost anything.
If a company runs a fleet of mobile technicians, they can pass variables to isolate transactions processed by a specific hardware terminal, right down to the device nickname.
They can query the API for every transaction processed by Ownit42 iPad between Tuesday and Thursday.
They can pull for specific invoice statuses, generating real-time lists of paid versus past due accounts.
It prevents the finance team from flying blind. It allows the merchant to ingest the gateway's truth directly into their own ERP or accounting software,
Automating reconciliation and providing real-time visibility into cash flow.
Without that programmatic access, managing the financial operations of a high-volume e-commerce platform would require armies of analysts manually cross-referencing spreadsheets.
It's the visibility that keeps the entire operation running.
Truly.
All right, let's bring it all home. We've traced the invisible architecture of online commerce today.
We really have.
We looked at how developers use the Quick-Click API to generate simple, custom-styled HTML buttons, utilizing mathematical hashing to secure the client-side data against manipulation.
While battling modern browser privacy features that break iframe integrations.
We looked at the intense liability of direct post, where handling the toxic waste of raw credit card data sources developers to rely on secure vaults, tokenization, and complex cryptographic payloads to handle Apple Pay and Google Pay securely.
We unpacked the brilliant routing of the three-step redirect API, letting sensitive data bypass the merchant's infrastructure entirely.
And we explored the strict, non-negotiable compliance rules of recurring MIT billing and how the Query API prevents accounting departments from losing their minds.
This raises an important question, and it's a dynamic we haven't touched on yet.
With that,
All of this incredible architecture, the tokenization, the biometric payloads, the background API handshakes, is designed to systematically eliminate friction. It makes spending money as effortless as a glance at your phone.
that is true.
But as developers get better at making these transactions entirely invisible, at what point does the technical ease of spending money outpace our psychological awareness that we are actually parting with it? When the friction is completely engineered out of the system, the mental speed bump of budgeting and financial consequence might just disappear right along with it.
That is a fascinating trade-off between technical convenience and human behavior. It definitely makes you look at that frictionless buy now button a little differently.
It really does.
Thanks for joining us for this deep dive into the invisible maze of online payments. We will catch you on the next one.